Okay, so up to this point, we've seen a lot when it comes to the current manual approach to corpus processing. We've looked at curating the corpus, entering a new item into a database, creating the structure for a content JSON file, filling in the JSON file with the contents. Now we're going to look at what's the point of even doing all this work? Well, remember the whole point of this project is that we're saying that the corpus-informed approach produces better translations. At least that's what we want to test. So we've got a script here, create vectors batch, that gets loaded onto, this and the config.py get loaded directly onto Google for use with Google Colab. So I'm just going to head over to an instance where I have this set up. I've got my scripts here. I've got my create vectors batch, my config file, and then I have my corpora over here where I've got it set up exactly the same as the local structure. So in my Spanish folder, I would want to replace my database here with the newest version, and then I'd want to add the new files to these two folders. Now I would add the gai-esp_item3.json. So then I head over to my scripts file, and essentially what I'm going to do is I'm going to run this notebook. What this notebook is going to do, this notebook takes the JSON files that we created and converts them to vectors using the GINA embeddings v3 model. So this is the steps that the notebook follows. It loads the required libraries. It loads and examines the database structure for both of the databases, Spanish and English. We'll need to update the notebook to handle the two new languages we're adding to the project. It loads unprocessed documents for batch processing. That is, I've already got some vectors here from previous times I've run the notebook, and I don't want to recreate the vectors that I already have. So the notebook is designed to look for which documents have already been processed, to exclude those documents in the next round of processing, and to only create vectors for the new documents that have been added to the folder structure. After that, we're just defining some text extraction functions, defining the vectorization functions, initializing our multilingual embedding model. Then the batch processing takes place and a HTML visualization is printed. You can go through and read through this notebook and test it out and do things like that. The whole point is that after we get through running this notebook, running each of the blocks of code in this notebook, we end up with a folder called GAI, and both Spanish and English vectors mapped to the same vector space. I'll be able to demonstrate these a little bit better from this file. So essentially, here's a section one from probably the attention is all you need paper. Here's the vector that the Jupyter program creates from that section. Then the next section is included. So what the notebook also does is each time we run a new batch of processing, a new batch of documents are processed, they're appended to the end of this file where the vector count is recorded. This was from GAI English item 001. That is indeed the attention is all you need paper. That's for the previous object. So again, this is just the JSON file that contains the vector, the actual text that corresponds to the vector, and so on. And we've got Spanish content around here somewhere as well. I think Spanish content is maybe at the end. Let's get up to here. Yep, so here's a Spanish section that we have the corresponding vector for. English and Spanish all getting put into the same JSON for the vectors that we have at different levels. What's kind of cool is the notebook also generates that HTML visualization report. So in HTML, the visualization, what's tricky about the visualization is that the vectors that we are creating are in 1024 dimensions. And in this visualization report, we're trying to visualize where the vectors are in the vector space in either 2 dimensions or 3 dimensions. What we're trying to get an idea of here is how semantically similar are these vectors? Because essentially this long list of numbers, this vector, is how the machine understands, and I'm going to put quotes around the word understands. This is how the machine understands the meaning of this text. For us as humans, we understand the meaning of the text based on the words on the page, on our interpretation of these words. What the LLM does is it converts those words into these vectors, which is a mathematical representation of the semantic meaning of the text. If it seems a little bit crazy to you that this set of numbers means the same thing that that block of text did, it seems a little bit crazy to me too. And there's actually future experiments that I would like to do on this. I would like to design a small application that converts text to vectors and then back translates the vectors to text to try to see what results from that. You know, when we do a back translation of human translations, we're typically doing something like that because we're working in like the pharmaceutical field or something like that, or where there's going to be test subjects. And so it's a part of the verification process that any content that is translated, let's say we're running a study in English and we're going to have some Spanish speaking participants, we would do a translation into Spanish and then we would do the back translation back into English so that the people who are running the study can have some sort of a verification that, listen, the translation means roughly the same thing as the original, though back translation is a very tricky topic because, you know, the content will always change when you go to the back translation. You're never going to get an exact copy of the original content you had translated through back translation. Similarly, when translating text to vectors and then back translating vectors to natural human language, the back translation isn't going to produce a text that's exactly the same as the content that was originally vectorized. And I'm just curious, however, if that process of text translated to vectors, back translated back to text, would help give some sort of a sense of what the machine understands semantic similarity to be. It's a very interesting question, and I really look forward to working on that back translator soon. What's interesting is because we're using the GINA embedding version 3 model, I tested out a few other language models, large language models, to do these embeddings that would have created embeddings at smaller dimensions than the 1024 that GINA produces. Unfortunately, there were just issues. So I think I tried like the Diletus model or something like that, and Hugging Face wouldn't allow the API to connect or something like that. And then I tried another model that can be used for multiple purposes, but the only API available to actually use the model was not to create vector embeddings, but to do some other type of large language model processing. And so I landed on the GINA embeddings version 3. It's a very large dimension size, or I guess it's a larger dimension size depending on, or in comparison to some of the previous uh, dimensions that I had tested. we have to keep the dimension size in mind once again, because what the vector embeddings are doing is they're embedding that semantic meaning on 1024 dimensions. This is a representation of just 3 dimensions. So there's a lot of inaccuracy in this representation here. Still, the 1024 dimensions is really good for creating document level vectors. It's somewhat good at creating section level vectors. It's probably overkill for the creation of paragraph level vectors, because paragraph level vectors, it's such a small amount of text that we don't need to represent this small paragraph in 1024 dimensions. It's overkill. So we could probably use a model that produces smaller vectors of a smaller dimension for paragraphs. But then again, there's also the issue of getting these systems plugged in with one another. And in my experience with the 2 other models that I tried, I couldn't get them plugged into my systems in the way that I wanted. So I used the GINA model for everything. Now here, what we can do is we can try to get a sense for what is semantic similarity from the perspective of what are points on this representation where 2 vectors appear close together. Here's a vector in English, here's another vector in English. Here's a vector in, let's see, English, English. I want to try to find a pair where it's English and Spanish that are close together. Here's a Spanish item. Here's kind of an English item, kind of close. So what's interesting here is that this section 3.1 from GAI-ESP underscore item 1, so item 1 in the Spanish corpus, is similar semantically to section 3.1 from GAI-ENG underscore item 3, so the 3rd item from the English corpus. Another interesting thing we could do is we could go find the sections, the text in the sections that corresponds with these section titles, and just look at the content and say, now why is it that these 2 pieces of text from 2 different languages are semantically similar? Again, we're mapping all languages onto the same vector space. So this is a mix of English and Spanish vectors. I wanted to do that because that's just what I wanted to do. There's no sense in, we have to think about what's the purpose of these vector embeddings in the actual system itself. In the actual system itself, the purpose of these vectors is to be able to conduct similarity searches later on. Remember when we put content, sample content in here and translated it, what the system is doing is it's converting this text to a vector, analyzing the source vector to the corpus vectors, and then pulling context, saying, this content in Spanish is similar semantically to this other content from the corpus in English. Let's pass that context to translation. So here's an English section that got passed. It was a thematic match. It looks like the age of AI has begun was the closest thematic match to the Spanish content that we put in. Content from documents that are topically similar to your input text. What's interesting is this content is from like an essay where somebody is in Spanish reflecting on like what's going on with these machines. Isn't this like very futuristic? And that's sort of what Bill Gates is talking about in his article, The Age of AI Has Begun, as well, just sort of reflecting upon AI and how it might be used. So it's interesting that the system found those contents to be similar through these vector embedding searches, passed this content to the DeepSeek model to inform translation, and then DeepSeek was instructed, listen, take the context that you've been passed into consideration when you're generating the translation that we're ending up with here. So the last step is once we get these vectors, and each time we get the vectors, I guess this is the last piece of manual processing that happens is we're manually adding the vectors here so that they can be loaded onto a person's browser when a visitor accesses the website and then used for those similarity searches. Thanks for following along with these videos. I know this got to be a little bit long, but it's an important topic. And if we're going to build in functionality to automate all of these steps that take us from one system to another system where we're having to manually upload and download files, if we're going to automate that, we need to have a good understanding of how is the work currently being processed. So we just understand the problem statement. We cannot solve the problem unless we have a solid idea of what the problem is. So these videos have had the intention of describing the problem.